So, hello and welcome to my talk. And hopefully, you are super well whenever you watch it and wherever you watch it. It is very interesting to give some talks in this online pre-recorded format, but hopefully, soon enough, we will be able to do these kind of conferences fully in person. So about me, my name is Levente Szabados. Originally, I'm a programmer, but then I went to do a detour to do some cognitive science and back then to industry. And my main industry focus when I went back was leading a research group in financial modeling and time series analysis, and then becoming a CTO for a startup where we did natural language processing. Currently, my focus is more on teaching. I teach at Frankfurt School of Finance and Management, and also on Avancité in Paris, which is a business school dedicated to artificial intelligence. And when I'm not teaching, I'm focusing on industry projects. And in industry projects, I'm also confronted with a lot of time series problems and a lot of solutions that require forecasting. So that's why I thought that a bit of a glimpse into the current state of the art of forecasting is in order. So let's just jump into it. From the perspective of forecasting, I think what we see is what we don't see. Okay, what do I mean by this paradox? I mean that there is this steady progress and nice communication from the community of computer vision that, well, there is a good benchmark that we can look at, which is, say, the ImageNet data set, and we see this very obvious steady progress, basically a saturation of a kind on ImageNet. So during the times, this is kind of the pre-deep learning era that is basically cut out of the image, and inside the deep learning era we see this steady progress towards a very common understood goal, however flawed it may be. Now, in time series domain, the question is not so simple. There is a set of benchmarks, or better to say, a benchmark competition that is being organized regularly. This is the M competition, the Makridakis competition, which tends to give some hints for the practitioners about what are the most promising modeling avenues to tackle in frames of a time series problem. But this is an interesting case since we do have this gut feeling that the diversity of time series problems is way bigger than, say, the ImageNet based image classification tasks would imply in case of an image domain. So we feel that the image domain, whenever something can do an image classification on a broad enough set, then it will have good coverage for our particular data set also. In time series, this conviction is not yet widespread. I would argue that it's not rightfully so. So I would absolutely push for and investigate the possibilities of more generalization power in the forecasting domain. Nonetheless, we still in our domain are very much focused on individual solutions of individual time series. That makes benchmarking a bit less of a focus, or less of the centerpiece of our struggle. And also the M competition itself is organized pretty rarely, in the sense of every couple of years, where a couple can be at points pretty long, like 5 years or so, meaning that there is not that much of a recent or frequent update that we can take to gauge the estimate, gauge the performance generally of many models, and also across, say, M4 and M5, the fourth and fifth installment of this competition, there was considerable reshuffle of the data set, so it's not that easy to compare. Nonetheless, my argument is that the introduction of deep learning into the domain of time series forecasting did have some effects. So say RNN, LSTM models that were applied to time series problems considerably helped in certain cases, though still there are a lot of open areas or open problems that have to be tackled. Just to name a few of these open problems is the interpretability of models, which can be of paramount importance in certain cases, is in general a thing that we have to use specific tool sets for. So the development of interpretability tool sets with respect to any time series model is always one of the concerns. Some kind of probabilistic forecasting instead of point forecasting had been worked on, even in case of RNN and LSTM models. Say deep AR is a model type that was basically the extension of RNN and LSTM to a probabilistic forecasting setting. Multi-step forecasting is always a challenge, so we have to understand that this is kind of an orders of magnitude more complicated problem than, say, a step one forecasting. So we are always having half an eye on this business relevant and practically relevant multi-step forecasts. But what we will be talking about today is well, the obvious in the sense of better accuracy. That we will look into some models that promise generally with some inductive bias or with some nifty engineering in the sense a better accuracy. And the second part of the act 2 of this talk will be about transferability. So that main characteristic or that main property of deep learning, that it is able to learn from one data set and reuse that knowledge at least partially to solve another data set, can be of crucial importance, and we will look into some of the problems or some of the challenges related to this with respect to time series. Okay, let's look at Act 1. What did people fiddle over and beyond with in case of RNN and LSTMs? Now, first and foremost, let me point out that that RNNs and LSTMs had some very nice competitive results, but it was not that domineering. So we didn't have the feeling like in case of convolutional networks, when they were introduced to the ImageNet competition, there was a sudden jump of 15%, 10%, and then sooner or later 15% of accuracy on the data set in a year or 2 years, which is like an amazingly, quite shockingly strong result. Now, what happened is that mainly as the M4, the fourth installment of the Makridakis competition showed, is that yes, well, one can get in general competitive performance with deep learning models, but also the classical models, say ARIMA, or these kind of totally non-deep learning, in many cases not even parametric models, fared pretty well. One of the takeaways when you look at the final elaboration or the final thoughts of the organizers of the competition was that the interesting result, the most interesting or the best results came from combinations or hybrid models, in the sense of taking some deep learning model and hybridizing it with some classical non-deep learning related model. So one of the things that are worth mentioning is maybe this dichotomy of, do we have to use deep learning or do we do classicals, is not a dichotomy at all. Maybe we have to combine these two approaches and merge their respective strengths to get to a nicer and more robust solution. Just as an example, let me just skim through the idea of a hybrid model that was the holder of the torch as state of the art for a little while. which is ES-LSTM. As name implies, it is a hybrid model. ES part is exponential smoothing in this case, and LSTM is Nomen est omen, is a long short-term memory network, meaning the main concern or the main idea here was that though generally the seasonal components and kind of a local linear trend can be estimated pretty well with classical exponential smoothing techniques, especially like the Holt-Winters add-on, so to say. So the version of exponential smoothing that takes into account levels and seasonal components themselves, which, by the way, can generalize pretty well in a structured time series. But the locally changing trend component is something that can go over and beyond the linear trend capabilities of classical models, and that's where the added benefit of introducing a recurrent neural network comes into play. So basically, the structure is taking an RNN and trying to model based on the residuals after removing the effects of level and seasonality, and that's how a more complex pattern recognizer as a recurrent neural network can contribute to the general performance by adding its own components to the forecast. This is, I think, one of the important topics that will recur on and on while we will be discussing next models that were elaborated by people, is that the decomposition of time series as a general approach is always the dominant way of thinking, and people try to produce models that are taking into account this decompose things that you can know and decompose things that are maybe more complex to be modeled, and put these elements together to get a good quality forecast for your domain. By the way, recently, since originally the ES-LSTM was a univariate method, recently multivariate version, which is called MES RNN. So basically the multi input exponential smoothing recurrent neural network approach was introduced, which is basically taking into account arbitrary many parallel time series, doing the classical exponential smoothing as basically capturing the things that a Holt-Winters style modeling can capture, and on the residual training some deep learning networks that are capturing more complex and less easily and less obviously modelable patterns across multiple channels, so to say, of input. Okay, so hybridization was one of the main driving forces in the M4 competition. But naturally enough, people were thinking and having this thought that the big revolution in deep learning with, say, computer vision came with the appropriate inductive bias, with the introduction of models that have structural properties that are appropriate for that specific domain of images. And how about trying to innovate more on the architectural side of deep learning purely, just to realize some performance gains? For this to be understandable, I mean, the directions that people took to be more understandable, let us just step back and think for a tiny little while what kind of biases or structural properties or inductive scaffolds do deep learning models in general have, or types of deep learning models can generally have, that helps in a time series domain. Now, one of the obvious and kind of new approaches to take is Well, transformers were super successful in the NLP domain. Why don't we apply transformers also in the time series domain? It would have a lot of nice benefits. Say, we could absolutely think of transformers and sequences of natural language utterances and sequences of time series elements as a pretty naturally similar looking or similarly structured data domain. So basically the potential of attention-based models to point and click at, so basically to choose points of connection with a pretty distant, pretty big distance amongst them, and combine information from the far past with the near past could be additional kind of benefit that we could realize. Also, the sparsity or the potential sparsity of attention layers can help to make models more interpretable, and kind of performance-wise, even the transformers themselves are more parallelizable than, say, RNNs and LSTMs in training. So we could even, from the pure computational resource perspective, realize some kind of gains. These are the potential benefits that we could encounter. Now, as a theoretical motivation for how does this look, how can we imagine this inductive bias of, say, transformers in a case of time series, we would have to somehow visually think about the other potential inductive biases. Namely, one of them is convolutions. One has to state that for a long while, or for a not insignificant current amount of work even, convolutions are competitive in time series domain. Why can this be? Convolutions, with some addition, two notable additions. One addition is so-called causal convolutions, in the case of not having a convolutional filter that is processing some elements left and some elements right from a given point that it observes. Why is this a problem in time series? Because the right part is always the future, and it would be rather nasty to try to process some parts of the future to be able to predict the present, which is not the business that we are at. So causal convolutions, which always take just a left context, so in our case a past context to previous a right, to process a right element, are one of the modifications that made modeling with modeling time series with convolutions more feasible. The other trick is dilated convolution, which is enabling the originally super local processing of convolutions, which is literally looking at a shortest possible window of 2, 3, 4 steps maximum, and combining information or detecting information in that window throughout the time scale of the whole processing or the whole time series, to be generalized on bigger and larger overarching structures. So dilated convolutions, as written, as demonstrated by this animation, where we don't just take at every layer, say, a fixed stride, or we are basically trying to manipulate the processing in a way that we cover a larger area of patterns and allow for the successive construction of larger and larger pattern sets to detect. This made convolutions pretty competitive in the time series domain. Though originally, let us be honest, the intuition is that convolution is good for neighborhood-based things, in the case of neighboring 2, 3, 4 points influencing each other. Whenever our time series has that kind of structure, it is pretty okay to assume that a convolutional network will have good performance. Or to put it more bluntly, whenever we think that the causal relationship don't stretch back in time a lot, just there are these local relationships that move the time series in a certain way, then convolutions are a natural way to go. But I think one of the big concerns and also already the motivation for recurrent neural networks originally was that in many sequences we do have this strong assumption that long-term dependencies are of interest. So RNN has this different inductive bias that it is basically capable of remembering, in case of an LSTM, for a pretty long set of steps, certain states. So it is basically summarizing and aggregating and re-aggregating, in a sense, the whole state of a longer sequence and carries it with it. Now, in certain sense, this is not unlike exponential smoothing methods or any kind of method which takes a longer and longer sequence with more and more dampening or more and more forgetting into account. So though it has the potential to be a long-range dependency modeler, it also has the problem that it has to carry over or push through the state variables that are remembering the current summary of the sequence through successive steps. So basically, it cannot jump over any processing step whenever it has to remember things, with the caveat that the gating mechanism in LSTM helps a bit or even a lot in jumping over information. But nonetheless, the main idea is still that information is dragged on through time in one way or the other. Now, attention mechanisms are a bit different. Attention mechanisms are for every time step parallelly processing every other time step, meaning that the paying attention or the inclusion of information for any arbitrary time point can happen from any other arbitrary time point that is part of the input. So this kind of whatever to combine with whatever came in very handy in case of natural language processing, since we can absolutely see that in certain languages, for example, the last words of a sentence were very strongly connected with some very early words of the sentence or some middle words in the sentence, and there is a complex behavior of what is connected with what, at least from the language perspective. From the time series perspective, this is kind of the direct opposite of the inductive bias of convolutions. Convolutions are super local, attentions are super global in the sense of, well, look at whatever you want by processing a single step. So naturally, one could argue that transformers are a more general framework that could revolutionize time series modeling. Now, let's very quickly skim through some of the problems that they encountered in this domain. So why not just slapping transformers on the whole thing and we are having a good day, we solved everything as in NLP? Well, yes and no. So yes and no, in the sense of already in case of natural language processing, it was a bit of disturbing factor that transformers themselves are not temporary aware or sequence aware. I mean, the parallelism that with which at every time point they can pay attention to every other time point is having the drawback that you explicitly somehow have to model in or factor in or give that information to the model that, hey, you are currently looking at the 10th element of a sequence, because just from looking at the sequences, it doesn't have this clue. So in case of natural language processing, positional encodings were introduced that try to convey the information for the model that generally it is somewhere in the time series, and generally it has to pay attention to combine the right things with the right things. In case of time series, the thing can be generalized in the sense of we are able to, or we can manually construct time embeddings or time encodings. We can use sine and cosine functions to basically manually, based on our perceived periodicity, say weekly, hourly, daily periodicities that we see and observe in the data set, encode time. Or we can use something like time to vec as an embedding layer, which is basically a self-learned set of weights and biases that are having a sinusoid activation function. So it is basically Fourier decomposing the time. So hopefully comes up with the right decomposition of the right periodicity. So yes, it is not completely obvious how one can kind of input the time information itself, and arguably this is one of the big points in time series modeling, that we are regressing on time. Okay, the other problem is that well, transformers are not cheap. Not cheap in the sense of they are quadratic in computation. This also had some problems in natural language processing, that since every time point is attending to every other time point, that means that we are basically having an attention matrix potentially. This is just imaginary, but a computation of everyone with everyone, so everyone squared. That means that without any additional techniques, we are pretty much bottlenecked on computation. Log sparse transformers, interestingly enough, so these kind of approximate transformers, so to say, which are saying, yeah, well, we shouldn't pay attention to every point and every other point, but we should, with a higher probability, pay attention to more local elements, and with lower probability to more distant elements, which is, by the way, introducing a kind of recency bias. So log sparse transformers came from this motivation of reducing computational bottleneck, but maybe they even introduced some useful bias in the recent things are more important sense. So this is one of the things that people are working on in the sense of trying to jointly somehow increase the performance, but also refine or introduce still acceptable or even maybe beneficial bias with this. Okay, but is this the end? So are we saying that you introduced transformers, solve these two problems, and that's it? No. No, in two sense. One sense is that hybridization is always looming there. So maybe the transformers can be also hybridized with classical models, but also a surprising thing happened, that full connections strike back. Full connections, fully connected layers, so to say, stride back in the form of n bits, and it's kind of a family of models, which generally is built on a residual architecture of fully connected layers. So no convolutions, no transformers, no RNNs whatsoever, but a conscious decomposition of layers of patterns. So it is basically a technique of doing joint forecasting and backcasting. So basically input reconstruction in every layer, every block, so to say, and these blocks are forming in one sense a forecast and the backcast, so a reconstruction of the previous time series and the forecast, whereby the forecast is utilized in an additive manner. So a layer is forecasting some elements of the future, some patterns in the future, and an additional layer will produce an additional forecast that is added together to compose basically the future. And from the past perspective, the things that are backcasted by a given layer are removed from the past, so that the successive layers can pay attention to residual, still remaining patterns that are to be captured. So in this sense, this is basically a harking back to the original concept of time series decomposition, but in a very nice neural manner. So what is interesting is that this thing also got generalized to multiple inputs. Okay, which is the n hits version of n beats. Okay, are we happy with the result? Well, I mean, it's not decided. The not decided part comes from two things. One is that that there is still some versions or combinations that we didn't uh, observe, and also we do have this feeling that maybe a dedicated specific architecture, say n beats for time series, is having the right bias, whereby some proponents of transformers say that it should be the general approach that solves vision and solves NLP and solves time series together. So it's undecided, but worth looking at. Now, for the last, say, 5 minutes, I will skim through some of the results that are opening up because of the application of deep learning to time series, namely transfer learning. I mean, one could argue, as Ian Goodfellow argued, is that the essence of deep learning is representation learning, is the ability to build up a rich, deep, complex hierarchical representation of a data set that is generally over and beyond that specific data set, capturing some rules of the game, some patterns that can be transferred from one point to the other, or one data set to the other. Now, the question is how we can realize these gains in these gains of transfer learning in time series forecasting. First and foremost, this is a pretty new field. It's gaining traction. So transfer learning with respect to time series, as now measured in the number of publications per year, is catching up. Why is this 7? It is 7 because the paper I cite this result from is on January or February of 2021. So that don't be frightened. It's not dropping back. It's just gaining traction. But also it's interesting that time series classification is one of the main drivers of this area. And in case of forecasting, it's still a pretty underutilized way of teaching on generally many data sets, a nice model, and then transforming those weights and trying to forecast your specific problem with it. Good. What are the challenges? The challenges are, as very well summarized by Gottfried in one of these wonderful posts that he had, is that one of the big challenges is that there is an obvious structural hierarchy in case of, say, images, whereby smaller local edges construct shapes that construct bigger shapes that construct objects, or also in language where words construct sentences and those construct paragraphs and so on and so forth. From time series perspective, it is always a bit more questionable whether it is sure for every time series that a local pattern is consisting, or a global pattern is consisting of more local patterns that repeat themselves in a deep hierarchical fashion. In some certain shallow sense, seasonality, trend, and remainder are components. In this case, n beats is not a bad idea, I have to say, so that the general motivation of n beats is obvious, but how deep this hierarchy goes is of question. Also, what inputs? So in case of multiple input scenarios, the number of input and the the meaning of the individual inputs can change drastically across data sets. In this case, some general univariate embedding methods or methods that are trying to forecast one single univariate data element of a data set, and those that can generalize and transform are maybe workarounds, but clearly this is making more fuss than one would imagine. And the third question is what to transfer from. Take every possible time series that you can lay your hands on and then transfer, learn from that. Or maybe there is a notion of similarity and the age-old understanding of transfer learning that the more similar the target data set to the source data set is, the better performance you are able to realize. Now, the huge question here is that what does it mean that two data sets are similar in the time series perspective? One way to try to do this is basically align or pre-align or measure the distance in time domain, in the original domain of a data set. Say, look for a time series that look pretty much like your current time series that you want to target predict. One of the works that I'm citing here is looking at specifically taking dynamic time warping or Jensen-Shannon divergence as and Jensen-Shannon divergence. So first the alignment and then the distance computation would kind of pre-filter for you the candidates that you should take into your data set that enhances the performance of prediction with respect to your target. Now, who tells you that this is the right way to go? Meaning that it's not the real question whether one can have similar inputs, but the question is how similar these are from the prediction perspective, so as outputs. There is a more elaborate way to go. So if you look at this very recent paper of relationship aligned transfer learning, in this paper, the authors argue that first you have to basically build up encoders of the individual data sets, and then in the encoder encoded representation, take that representation, save with a linear probe, and try to measure first the similarity in the encoded space among time series, and then the predictability distance or predictability similarity to your specific target set. So you successively choose the data sets, but based on a deep representation and not in the original time domain. Now, this becomes a pretty tedious 5-step approach of first encoding things, then selecting similar things in your encoding, and then trying to predict the target, and then choosing the most predictive elements, and then jointly retraining everything, and so on and so on. So basically, this algorithm is a pretty fidgety or pretty complex way to do transfer learning. It does work in the sense of it achieves state-of-the-art results in a pretty wide. So basically the M3 data set, not the current M5, but the M3 data set of data sets, basically. But I would argue that this is a pretty complex method compared to what is basically happening in case images and image-based transfer learning. So for not that radical amount of gain over, say, n bits, one has to do many steps. So one has to be aware of or conscious that given their own data set, whether this is worth it or not. Generally, some promising results of deep transfer learning with respect to time series came out also. So in another survey-like paper, people try to re-implement multiple approaches, namely convolutional networks, temporal convolutions, and LSTMs in a transfer manner, and it showed consistently that there is something to be gained in the transfer learning scenarios. So there is promise. There is promise. I would absolutely argue that one has to kind of keep an open eye for all the new architectural advancement, and together with that all the transfer learning abilities, since if we can realize transfer learning in our case, in our domain of time series, it will give a big boost to our performance, hopefully. But our ImageNet moment didn't arrive yet. So some people are still skeptical. There is also a very recent paper that argues that maybe this whole deep learning thing is not at all that dominant, or by its nature cannot become super dominant in the field of time series. So I think we live in exciting times with respect to having a lot of innovation that we can work with, and but hope that we can try to innovate on the cutting edge and try out these techniques with high benefit from the business perspective, but also with some contribution of understanding, so we can make even some contribution to the general understanding of what the right way of modeling time series is. So with that, I thank you very much for your attention, and the notebook I will try to make available so that you can skim through all the details that I was just rushing to cover. And I'm very grateful for any comments and feedback that will reach me via different channels. Thank you very much for your attention.